till now we have discussed three kinds of unsymmetrical faults. First was the single line to ground fault, the second one was double line fault, and the third one was double line to ground fault. Now all of these faults were kind of shunt faults which were creating some kind of unbalance in a balanced three-phase system. Now in this lecture we will try to study another kind of fault which also creates an unbalance in the system, and that is the opening of conductors. Let us say if I have a three-phase system which is balanced at all other places, represented by, let us say, just by these three lines. This is A dash, B dash, C dash. Okay. Now, if there is, let us say, some fuse in the circuit and this fuse gets blown only in this phase, then again it creates some unsymmetry or unbalance in the system, which is clear that phase A is now open. So it indicates that we can analyze this kind of system using symmetrical components. Similarly, if there are two phases open, then again there is an unbalance in the system. We can easily analyze this kind of system also using sequence components or symmetrical components. So first we will try to see the first case in which only one phase is open, that is one conductor is open. Now this kind of situation can arise whenever, let us say, only single fuse is blown, or we have single pole breakers with auto reclosing facility such that only one pole of the breaker opens and other two poles are not opened because of the fault in, let us say, at this point. So this is also kind of one phase open or one conductor open situation. Now let us try to analyze this situation. The voltage at this point is VA and at this point is VA dash. Okay, with respect to ground. So we can see that VAA dash, we don't know what it is. VBB dash is equal to 0 since it is just a short circuit. VCC dash is also equal to 0. Now these are some three equations. Similarly, IA is equal to 0. Since this phase is now open, then IA is equal to 0 for this case. Now let us try to find the symmetrical components of VAA dash. Now we know that VAA dash 0 is nothing but 1/3 of VAA plus VBB dash plus VCC dash. Now these two are equal to 0, so it is equal to 1/3 VAA dash. Similarly, VAA dash 1, that is the positive sequence component of this voltage, is 1/3 VAA dash plus A VBB dash plus A square VCC dash. Now again these two are 0, so it is nothing but 1/3 VAA dash. Similarly, we can see that VAA dash 2, the negative sequence component, is also equal to 1/3 VAA dash. So from this we see that this voltage, the zero sequence component of the voltage, the positive sequence component of the voltage, and the negative sequence component of the voltage are equal. All three components are equal, and we also know that IA is equal to 0, that is IA0 plus IA1 plus IA2 is equal to 0. So let us say these three equations are equation A and this equation is equation B. Now these equations are trying to show us how to connect the sequence component at the fault point. So at this fault point, these are 2 points, A and A dash. Okay, so at this fault point, how to connect the various sequence components? These equations are trying to show us how to connect them. Now let us draw the equivalent circuit or the equivalent connection. Let us say this is the positive sequence circuit with A dash point. Okay, the voltage across this point is VAA dash 1. IAA dash 1 is leaving and IAA dash 1 is entering. Similarly, let us draw, this is the positive sequence. Let us draw the negative sequence part. This is the reference bus. These are the 2 points A dash, and this voltage is VAA dash 2. This is current IA dash, or instead of writing IA dash, I will just write IA. Okay, since it is just clearly showing the direction of current. IA2 is leaving and IA2 is entering. Similarly, let us draw the zero sequence component or network. This is the negative sequence network and this is the zero sequence network. This is the reference or the ground. A dash, this voltage is VAA dash 0 and these are 2 points. Current leaving is IA0, current entering is IA0. Now these are the 3 sequence networks which I have drawn for this given system. Now let us connect them. We know that this voltage is equal to this voltage and this voltage is equal to this voltage. All are equal. So we will have to connect them in parallel. Okay. Similarly, IA1, IA2 and IA0, these all are adding into 0. So this shows us that if we connect the sequence networks like this, then we can easily see that this network is satisfying equation A and B also. So for single conductor open fault, we will have this kind of interconnection of various sequence network. Now in the next slide, we will see the second case in which phase B and phase C are open and phase C is not open. That is 2 conductor open fault. Let us say somehow there is a breakage in these 2 lines. Okay, so what will happen to that case and how to analyze this using symmetrical components, that we will see in the next slide. Now let us analyze this condition. VAA dash is 0. We don't know the value of these 2 voltages. Okay. Now we know that IB is equal to IC is equal to 0. This is IB, this is IC and this is IA. Due to the open conductor fault, these 2 current are 0. So IA0 equals to 1 by 3 IA plus IB plus IC. So it is equal to, these two are 0, 1 by 3 of IA. Similarly, we can clearly see that IA1 is equal to 1 by 3 IA and IA2 is also equal to 1 by 3 IA. So you see that all the sequence currents are equal. Let us say this is equation number A. Now we see that VAA dash is equal to 0. That is VAA dash 1 plus VAA dash 2 plus VAA dash 0 should be equal to 0. Let us say this is equation number B. So this equation number A and B is trying to show us that somehow if we connect these sequence networks in series, then we can analyze such kind of situation of having two conductors open, two phase conductors open by symmetrical component theory. So let us connect them. Now I have drawn these three sequence components and now I will connect them in series. This will connect like this. Current will enter and current will leave from this point. Now again in this sequence network, current will go like this. Current will enter from A dash and it will exit from this point. So in this way, what I have done, I have connected these networks in series. We can clearly see that current IA1 will enter into the positive sequence network, leave from this, then it will enter into the negative sequence network and then leave from this, enter into the zero sequence network and will leave from this. Now IA1 is equal to IA2 is equal to IA0. We can clearly see from this point also, this is IA2, this is IA0. So we can clearly see that these are equal to 0. Similarly, the sum of voltage VAA-1, VAA-2 and VAA-0 is equal to 0 in this interconnection of sequence networks at the fault point. Okay, so in this way we can analyze the condition of two conductor open in a three-phase system. Now we will try to solve a numerical example to understand how to utilize the concept of symmetrical components in analyzing single phase conductor open fault, and we can also extend it further to analyze the numerical example for two phase conductor open faults also. Let us see in the next slide. Now we have seen a similar numerical example consisting of this single line diagram in our one of the previous lectures. Now let us see what is the scenario given in this numerical example. We are given that there is a three-phase synchronous generator. This is the generator which is grounded through a reactance, and we are not given the value of this grounding reactance. Okay, we are told that its synchronous reactance X is equal to 1 per unit, the negative sequence reactance is 0.1 per unit, and X naught, the zero sequence reactance, is 0.05 per unit at a base of 7500 kVA and 4.16 kV volt. Okay, now we are given that there is a star delta connected transformer with solidly grounded neutral of the star side with 7500 kVA as base VA and 4.16 over 600 volt ratio. Its leakage reactance is 0.1 per unit. Now we are also told that there is a motor which is giving a 5000 HP or driving a 5000 HP load at 88% efficiency and 0.85 lagging power factor. The various ratings of the reactance on 7500 kVA base and 600 volt base in this side of the circuit are given as the synchronous reactance of the motor is 1 per unit, the negative sequence reactance is 0.3 per unit, X naught, the zero sequence reactance, is 0.06 per unit, and this grounding reactor is given by 3 times of this value is 0.09 per unit. Now we are given a scenario that it is giving this load, let us say what happens that at this point P or on the terminals of the motor, one of the phase conductors, let us say the phase A, gets open at this point P and remaining phases are closed. Now we are asked to know whether the same motor can supply the same load of 5000 HP at the same efficiency if this phase A conductor is open. We are also told that we can assume that excitation of both the machines is constant. Okay, now we will have to solve this question. First we will see what is the assumption. Here it is assumed that excitation is constant for both the machines. What does it mean? That, like we have seen in the fault analysis of synchronous machine, we see that during a fault the positive sequence reactance, the negative sequence reactance, and the subtransient reactance or the transient reactance or the steady state reactance come into the picture depending upon the time we are trying to investigate. So now we are trying to investigate the steady state scenario, that is whether it can supply the load or not. Okay, so it is clear that at this point this thing is clear that we are going to use the synchronous reactance of both the machines. Okay, now as we know that during a fault the voltage behind the subtransient reactance or the transient reactance or the steady state reactance is going to remain constant if the excitation is a constant value. Similarly, EM dash or EM double dash or EM will remain constant at their prefix value, prior value, if excitation is constant. I have also made a detailed video, and that video is available for the model of synchronous machine during the fault if it is carrying some load, and that video is available on the playlist of having advanced topics in power system named playlist. Okay, so as of now what we will assume that since excitation is constant, then the voltage behind the synchronous reactance, since we are dealing with the steady state case, so we are just dealing with the synchronous reactance for the generator, and this voltage behind the synchronous reactance for the motor is going to remain constant. That is, the terminal voltages for this thing, so or this EM or EG are going to remain constant. Okay, depending upon the terminal voltage and the load current. So we are told that this machine is giving earlier a load of 5000 HP at 0.8 power factor lagging and efficiency of 88%. From this we can calculate the load current. (5,000 HP into 0.746, it will convert into kVA. Okay, now we will divide it with the power factor and with the line voltage, √3 into the line voltage. Okay, √3 VI power factor, and this thing is going to give us the line current. Okay, so if I again divide it with the base value, now I base, and this current is going to be lagging, minus of cos inverse 0.85. Okay, now I base, I know that in this side of the circuit is 7500 kVA divided by √3 600. So I can find the load current in per unit using this equation. Okay, and I already found it, and it comes out to be 0.566 minus J 0.351 per unit. Okay, so this is the load current. Now from this we can find Eg, the voltage of the synchronous generator behind the synchronous reactance, is equal to the terminal voltage, the rated voltage, terminal voltage 1 plus J1, this is the synchronous reactance, into the load current. So Eg will be 1.52 angle 24.2 degree per unit, and Em will be 1 minus J1 0.566 minus J 0.351, and it comes out to be 0.86 angle minus 41.1 degree per unit. Okay, now I have found these two values. Now let us draw the equivalent sequence network for this system, and we will then interconnect them according to the scenario of the fault. That is, this at this point P, one of the phase conductor, let us say of phase A, has opened, and phase B and phase C conductors are normal. Okay, so first we will draw the positive sequence diagram. For the positive sequence, this is the reference bus. Here comes the generator, Em. Clearly see that we are not using Eg double dash, we are using Eg, which we have calculated here. This is the synchronous reactance J1 per unit. This will be the reactance of the transformer J 0.1 per unit. Okay, now we will see the motor side. We will use Em instead of Em double dash. Let us write the values also. Okay, now this is the synchronous reactance of the motor J1. Now this is the point A dash. This is the positive sequence network. Okay, now let us draw the negative sequence network. It will be the similar to the positive sequence network, just the difference will be we will short these voltage sources and convert these values of reactances to the negative sequence reactance values. So it is x2 is equal to 0.1 per unit, J 0.1. For the transformer it is same, 0.1 per unit, and this is A. X2 is equal to 0.3 per unit. This is A dash. This is the negative sequence network. Now let us draw the zero sequence network. In the zero sequence network, this will also come into the picture. Let us say this is XM, or let us say XG. Okay, so it will be 3 times of XG. We don't know its value. We will later see that it is also not required in calculations. And here comes the zero sequence reactance of generator. X0 is equal to J 0.05. Okay. Now comes the reactance of the transformer. It is again 0.1 per unit, J 0.1 per unit, and this point is shorted to the bus, reference bus, and this is the line. This point is A. You should clearly know how to draw the sequence diagram, the zero sequence diagram for the circuit. It will be very easy to draw if you have seen my previous lectures. Okay. Now let us go to the motor side. 3xn equals to 0.09 per unit, J 0.09, and it is equal to x0 equal to 0.06, J 0.06 per unit, and this point is A dash. Okay, now I have drawn the positive sequence network, the negative sequence network, and the zero sequence network. The only thing remaining is to connect them at the fault point according to the scenario of the fault. Okay, now let us see what is the scenario of the fault. Here phase A is open. Okay, now when phase A is open, what does it mean? It means that the sequence components will be connected in parallel. We have seen in the previous slide only, in this lecture only. So these are the sequence networks. Okay, this is also connected. It doesn't matter whether you connect now A to A dash or A dash to A for these two. Now you can clearly see that the zero sequence current cannot flow because this circuit is open now. Okay, so clearly the zero sequence current cannot flow. This current is not going to return. It will go from this to this, and it is going to return to this only. So zero sequence current cannot flow. From the interconnection we can clearly see this. So we do not need to show this in our interconnection also, so that we do not get confused with various interconnections. Okay, so this is the interconnection of the sequence networks. Now first we will find what is the value of the power which this motor is going to receive in the normal scenario. In normal scenario, it is driving a load of 5000 HP, or if I multiply it with 0.4746, I will get the kilo in the watts or kilowatts. Okay, and kilowatts are converted to the input kilowatts using the efficiency. Okay, so this is the input power this motor is getting in the normal scenario, and if I convert it to the per unit by dividing by the volt ampere base, I get the per unit input power to the motor in normal scenario, and it is equal to, I have calculated it is 0.565 per unit. Okay, now the question is asking whether now this motor can take this much power, okay, from the system when this phase A is now open. Now you see, this connection has reduced to this thing, okay, that current will come out from A dash, A of the positive sequence, either it will enter to this point or this point, it doesn't matter, and it is going to circulate in this and come out from the other point and enter into the A dash of the positive sequence network. So even if we were going to connect in parallel, let us see if we were actually going to connect this in parallel, this would have been connected to this point and this would have been connected to this point only, and it will be A dash. Okay, so again current is going to enter like this, go and come like this. Okay, so you see, now we can easily find the per unit power which this motor is going to get from the system. How? We have seen it is a scenario in which there is this one voltage source, this is other voltage source, and in between there are reactances. Now we know that for such a scenario, we know that power is given by voltage 1, voltage 2 over the reactance between them into sine of the delta between these two voltages. This we have seen many times. This equation is already derived in this course only. Okay, so now the power which this system is going to deliver to the motor in the present faulted scenario can be found out. This is the positive sequence or the normal scenario voltage behind reactance of the generator. This is the positive sequence or the normal scenario voltage behind synchronous reactance for the motor. This will be the reactance, total reactance which this system is going to see. This is the total reactance. That is J1 plus J.1 plus J.1 plus J.1 plus J.3 plus J1. Let us write it. 1 plus 0.1 plus 0.1 plus 0.1 plus 0.3 plus 1, or it is equal to, and sine of delta, it is Eg Am over 2.6 sine delta. Now we have derived the value of Eg and Em. On putting, we will get the power is equal to, let me erase this, on putting the value of Eg and Em, I will get power is equal to, in per unit, 0.503 sine of delta, the delta angle between Eg and Em. Okay, now initially it was delivering power 0.565 per unit. Now we will compare that this is the possible power in the faulted scenario and it is the power in the normal scenario. You can clearly see that in no case the motor is going to get this much power, because for this much power to be delivered to the motor, this delta, this sine delta should be equal to 0.565 over 0.503 and it is equal to 1.12. That is, it is greater than 1, which is not possible. Sin delta cannot be greater than 1. Okay, yes, so we can clearly see that on opening of one phase of the motor terminal, the system is not able to deliver the power which was there in the normal scenario, and there will be reduced power depending upon this delta. Okay, so in this way we have analyzed open conductor fault also in this lecture. In the next lecture we will try to solve unbalanced system using symmetrical components, although that topic will be concerned to network theory or circuit theory, but since we are going to solve the unbalanced network using symmetrical components, so I will take that lecture in the next video only. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.